Hey guys, it's John Endem, and today we're going to talk about my final project, which is optimization. Optimization is a very useful skill to have in calculus. You can minimize the surface area, volume, perimeter of any object, and if you're talking about business, you can maximize profit while minimizing the cost. The key to optimization is to understand that there's very many different combinations of lengths or prices, whatever, which are represented by a graph. In this case, we have a downward shaped parabola. In order to minimize or to maximize, you have to find the derivative and set it equal to 0, which will give you the tangent line, which is shown above. So we're going to work a problem that will help you understand this concept. Find the area that will minimize the cost of metal in a cylinder that can hold 250 cubic centimeters. Okay, so for problems like this, you're going to want to have formulas. So 250 cubic centimeters is volume, and it wants us to find area. So we're going to need to write eventually the formulas for the volume and area of a cylinder. But before that, we need to draw a picture. Okay, so the cylinder has a height h and a radius r. Okay, so now we can write the formula for the surface area of a cylinder, which is 2 pi r squared plus 2 pi r h. And we can also write the formula for the volume of a cylinder, which is pi r squared h. So the reason for writing out both of these formulas is because we have two unknown variables that we can now simplify into one variable. If you notice, the 250 centimeters cubed is a measure of volume, so we can plug that in for the volume formula and solve for either r or h, and I chose to do h. So now we have the h value in terms of r, so we can plug that back into our surface area formula to only have one unknown variable. So instead of the surface area formula now being 2 pi r squared plus 2 pi r h, it's actually 2 pi r squared plus 2 pi r times 250 over pi r squared, which we can now rewrite as 2 pi r squared plus 500 r to the negative first. So now that we have this formula, we can take the derivative, which comes out to be 4 pi r minus 500 r to the negative second. So this is the most important step of optimization. So once you have a derivative formula with only one variable, you set that equal to 0. So what this does is it takes the slope of the tangent line and makes it 0 or flat so that you can find the minimum value. In this case, we'll find the minimum value of the r, and then we can solve for h. So now that it's set equal to 0, you can rearrange the formula so that it's a cross multiplication, since it's easier to do that with the negative 2 power. So that comes out to be r cubed equals 500 over 4 pi. And this can easily be simplified into 125 over pi. You take the cube root of that, and you get 5 over the cube root of pi, or just 5 times pi to the negative 1/3 power, which will get you 3.41 centimeters. So now we found the minimum r value. So if you recall, earlier in the problem we said that h equals 250 over pi r squared. So if we plug in r, or 3.41, we get the h value, which is 6.83 centimeters. So now we have the dimensions of this cylinder, so we can just simply plug in these values into our original surface area formula to find the area. So in plugging in these numbers into our original surface area formula, which is 2 pi r squared plus 2 pi r h, we get 219.4 centimeters squared. So this value uses the least amount of material. It's got the smallest dimensions possible that fit the parameters of the volume, which means cost is also minimized. Thanks for watching.